So the usual title that I use for this talk is, what is this thing called AI? So it's a callback to an old pop song. It's called, what is this thing called love? Okay. So, but then I was asked to talk about demystifying AI today, so I just kind of tagged it on as the additional title on top of that. And so I was a little concerned about giving this talk today here. Because everyone was talking about data standards and everyone is talking about the adoption of AI and things like that. And I'm going to be here, trying to give an introductory talk on AI. And the second thing I was a little bit concerned about was that I'm also was going to sound a cautionary note on AI, right? But I don't have to worry about that anymore. So let's go on, right? So what's AI? There are like two different viewpoints of AI, depending on where you come from. So AI is like this. Let me see if I can get. Okay, I can't get a pointer here. So AI is this menace that is coming to kill you and wipe out human race, or AI is this panacea that is coming to cure all your evils, right? Right. So that's going to solve all the problems that you have, right? What's the truth? That's the truth, right? It's neither, right? AI is a piece of software. Right? So it depends on how you use it, right, and what kind of applications you put it to, and channeling John Oliver again, it's going to reflect what you want to do with it, right? So it's not magic, it's not evil, it's not good. There's nothing of those attributes that people associate with AI. It's just a piece of software, right? So if it's just a piece of software, why should you care about AI? Right? You should care about AI because it's in everything, everywhere, and all at once. People are talking about AI. Right? So you can see that all kinds of applications, driving, speech. In fact, I jokingly say that kids of this generation are more used to talking to AI than to human beings. Right? They're happy talking to their phones and Alexa and things like that. Right? And also there are other areas like, in bail decisions, in courts, and in financial domain, AI is being used a lot. And more importantly, unlike in some of the healthcare applications, in many of these BFSI, banking-style applications, the scale at which AI is deployed is so much, it's even hard to get human oversight into it. Right? So those are things that we have to worry about. Right? Again, going back to the theme, AI is everywhere. So here you see stories about AI helping with chemical reactions, nuclear fusion, solving mathematical theorems that people haven't looked at, haven't been able to crack for decades. And of course, more the big news was helps solve the protein folding problem, right? So all of these are there. And of course, we've heard enough of the applications of AI in healthcare now. I just picked up a few things, including stories that say things like, AI solution beats Stanford radiologists in chest X-ray diagnostic comparisons, et cetera, et cetera, et cetera. So why are we talking about AI? Right? AI is not new. Right? It goes back, in some sense, to 1950s when Alan Turing said, "I propose to consider the question, can machines think?" Right? So, and then he came up with his own answer, which is popularly known as the Turing test nowadays. But Turing himself called it the imitation game. Okay. So the field was invented back in 1956. At least the term AI was coined in the year 1956, and there was a group of people who met in the Dartmouth College and then had this conference, and then they set out to create a field, right, that can describe the principles of intelligence so precisely that a machine can be made to simulate it, right? Just made to simulate it. It's not that they're talking about the machine becoming intelligent. Right? From the very beginning, right, replicating human behavior has been kind of been the hallmark of AI and artificial intelligence, and of course, saying that is like saying that integration is repeated addition. So it's a lot more complicated than that. I'm just simplifying things a lot for the audience right now. So AI itself, as we know, goes back to the 50s, right? And let's talk about AI hype that everyone is living through now, right? AI hype is not new. Right? Some of you might have seen this. In fact, I've heard multiple people tell me that they've heard me give talks online. So you almost certainly have heard me talk about this before. Here is a news clip, right? The Navy revealed the embryo of an electronic computer today that it expects will be able to walk, talk, see, write, reproduce itself, and be conscious of its existence. Right? So any guesses when it came, the news article? It's from 1958. Remember, the field itself, the word AI was coined in 56. And by 58, we were up and running. The hype machine was up and running. Right? So again, we'll come back to why are we talking about AI again in a big way now. But real AI success is also not new, right? There were people back in the 50s were sitting in front of a computer and then playing chess and checkers and other things live on TV, right? And some of us have heard this, remember this chess computer beating Kasparov, right? I felt very happy when the computer beat Kasparov. You know why? Because the previous year, Anand had defeated that computer, that AI program. Vishwanathan Anand had beat the AI program, and then the AI program went and beat Kasparov. And I thought this was the only way Anand was going to beat Kasparov back then, right? So every other head-to-head match he was losing, right? And of course, some of you might remember this IBM's Watson engine, which essentially was able to play a very general open-ended quiz game called Jeopardy, right? And so in 2011, it kind of literally was wiping the floor with the human champions in Jeopardy. And what was really amazing about this is at that time, IBM claimed that this was a general purpose AI system because it could just answer any questions about any subjects. I know some people in the audience are already laughing. So we know how badly Watson failed later. But at that point of time, it was considered an amazing breakthrough. So actual success stories are also not new, right? So let's try to understand what is really happening nowadays that's making us more and more, enamored of AI. So the way I think about it, right, there are multiple components to intelligence, right? So there is this question of perception, right? And then there is this question of cognition, right? So perception is just being able to take in the information, and cognition is kind of trying to organize it and make sense out of the information, find meaning in the information, right? And then reasoning and decision making, right, where we use kind of logic, you do some planning, and you want to recommend things to others, and all these kinds of decisions that you can make, right? All of this. And then the final component is learning and adaptation, right? So how do you learn from examples or learning from a teacher and so on and so forth, as opposed to being told what to do, right? As opposed to somebody writing down step by step what should be your process by which you are perceiving things or whether you're understanding things or making decision making. So the recent excitement in AI is all because we have made significant strides in learning and adaptation that is allowing us to answer all the other three components of intelligence also. We seem to have come up with a mechanism that is able to build this generally intelligent system just by learning from examples, learning from scratch. Right? That seems to have really, woken up all the latent science fiction theories in our head, and we think that AI is going to solve all the problems for us. So that's where we are at. So what is machine learning, right? So what is it that we say that a machine is learning, right? So that's what seems to be the crux of AI nowadays, right? So machine learning is a very simple idea. I'm not going to get into math. So don't anyone, if you're out there thinking that, oh my God, IIT prof is going to start with a few equations next. No. I believe the equal symbol doesn't even appear in any of my slides. So I think you can all relax. So the idea is, I'm going to give a bunch of examples, right, to the machine or to the program that's learning this, right? So the way it will work is, okay, if I give you this example, right, you have to say that it is an airplane. Right? That's basically what it is, right? Or if I give you this example, you have to say it's a bird. If I give you this, it's a cat, so on and so forth. So I'll give you these Can people see my pointer move, right? Okay. Wow, okay. The pointer is much darker on that screen than on my laptop screen. You can see it move. Okay. So I give a bunch of examples like that, right? And then the machine automatically, there's a program there that automatically learns the decision rules, right? That tells me, given an image, what should I classify it as? Think of a human being sitting down and writing rules like, okay, if it has 2 wings, right, and it's flying very high in the sky, then it's probably an airplane, right? And if it has feathers on it, then it is probably a bird. So somebody sitting down and writing rules like this, it's going to be very hard for you to come up with. If somebody asks you, can you describe an airplane so that a third person, when he looks at a new object, can find out whether it's an airplane or not? It's very hard for us. But there's a machine that can just come up with these rules, right? And this simple idea of saying that I can derive decision rules just by looking at examples has been what is driving a lot of the current AI innovations. So it all started off with this competition called ImageNet that has been running for several years, where this example is taken from, right? So you give like 1,000 different categories, right? 1,000 different categories. I've just given you 10 here, but you have 1,000 different categories and hundreds of images from each category, and you have to learn a rule, right, for classifying a new image into one of the categories, right? So on the y-axis you see here is what is called the error rate, right? What fraction of the images I get wrong. Right? So back in 2010, we were getting nearly 30%. The winner of the ImageNet competition was getting about 30% of the images incorrectly. Right? As time went by, suddenly you see that around 2012, there's a huge dip. Right? So suddenly from 25% error, we went down to 15% error. And then year on year, we improved so much that by 2015, we were able to do better than what's the base human error rate, which was about 5%. Right? So the 5% is the amount of mistakes that humans were making, and the computers were able to get better than that. Now that started the hoopla, right? It's a whole superhuman performance. Computers are so much better. AI is so much better than humans on at least some subset of problems, right? So that's where we were at. So what really changed? So what caused us to do this? And so many of these, so most of you know the answer because we have been hearing it from the beginning of today, right? So part of it is data. Right? So many of these AI systems that we build have three components to it. There are algorithms that allow you to learn these decision rules. There is data based on which you learn these decision rules. And then finally, you have computation power. Right? So how fast your computers are, how much data can you crunch, and so on and so forth. So what changed was essentially everything. So you started getting better algorithms, right? You got more access to more data because so much more digitization was happening, or digitalization was happening. You got access to more data. And finally, there's a significant increase in the amount of compute that was available to you. In fact, one can even argue that the algorithms themselves did not change a whole lot. In fact, some of the most popular, most successful algorithms that we use today were all proposed in the 80s. They were not new, right? So it's not that the algorithms themselves changed significantly. It's more because of the data and computation. And then we got into all these buzzwords that people use, like deep learning and neural networks and all that. Right? And there were three people who drove this innovation largely. I wouldn't say that three are the only contributors, but in some sense, Jeff Hinton and Joshua Bengio and Jan LeCun recently were given the Turing Award, which is the equivalent of the Nobel Prize for computer science, right? So for their contributions to deep learning. So here is one example of how this thing works, right? There are many, many such algorithms. It's just giving you pictures here, right? If you look very carefully, there are no equal sign on the. So this is an architecture that is inspired, presumably, by the visual cortex, right? So where there are what are called quote-unquote neurons that have a very limited receptive field in the input plane, and then they kind of fire whenever certain kind of feature is present in the input, and then finally you put all the features together and come up with a categorization, right? And the amazing thing is you don't have to define any of these features beforehand. So what happens is as you keep repeatedly showing these images and running your algorithms, we call this as learning, right? It learns representations. So it starts off by learning simple things like corners and edges, and then maybe like little color combinations, and then it starts learning small pieces of the objects. And then finally, it starts putting things together. You can see that there are dogs here, and there are flowers here, and these are birds, and so on and so forth. So it automatically learns these kind of features over time by repeated presentation of these examples, right? So that's, it's called deep learning because you're doing this multiple layers of thing, and so people just went crazy. So I just showed you something with 5 layers, and then people went 8, 19, 22, 150, so at 150, I don't think we can call it inspired by the visual cortex anymore. But still, these methods just do well, right? So where are we going with this? Not just images, right? Speech recognition. We're talking about how good it's doing in speech recognition. A lot of the recent improvements in speech recognition, including many of the things that are being done in the Bosch project and things like that, are driven by the advances in deep learning, right? Creativity. Here is some artistic applications. You can take doodles, you can convert them to paintings, and so on and so forth. And here is something somebody sent me last Diwali. So he gave this prompt to this tool called Stable Diffusion, Diwali on the Ganges, and give me a picture in the Van Gogh style, and then it gives you this, right? And so you can do things like that. So here is another example, which is slightly different in Turner, right? It's a game called Go, which is a very hard game to play for computers. And then there's this company, DeepMind, that built this Go player that could beat humans, right? What was important was it was trained in a slightly different way than all the database things that we have been talking about. It was actually trained with no data. It just trained from scratch by playing against itself, right? And it came to a point where it could learn moves that humans could not even make any sense out of, right? Not that it always works, but in this particular instance, it actually did things like this, right? So here is a very famous move called Move 37 in one of the games that the AlphaGo engine played against a human. And so the commentators went like this: that's a very strange move. And another person said, I thought it was a mistake. And then Lee Sedol, the person who was playing this, took a whole 15 minutes to formulate a response. They just couldn't make any sense out of what the computer was learning. All of this is great, right? In fact, this is a slide I had to add. This came about 2 weeks back. Can you read the headline? Man beats machine in Go, in human victory over AI. So what is newsworthy has completely flipped, right? There are some sub-areas where AI is doing so good, you're getting newspaper headlines when a human being beats the AI, right? So it's like crazy stuff. And of course, you can also get things like ChatGPT. Everyone is talking about ChatGPT, right, nowadays. Here is an essay. It's like amazing, right? Space exploration beyond the solar system. And I'm happy to share slides and things like that. People can read the essays, and there's so many of these out there on the web. ChatGPT does a great job. But what is amazing is that it's still the same idea that we had earlier. It's still learning from examples, right? And a little bit of fine-tuning is happening with some human feedback and reinforcement learning, like the Go engine, but still the same idea, right? Nothing fundamentally different. Except that instead of using the convolutional model that we talked about earlier, it's using something called a transformer. It's a different architecture underneath it. But what is the data that it is learning on is just this, right? So what is AI good at? In my opinion, AI is good at tasks where the cost of failure is not high, right? You can leave it like Alexa, right? So if Alexa doesn't recognize what song you want it to play, you're just going to repeat it, right? I mean, it's not like the end of the world. But then where there is really life or death decisions involved, AI is still not ready to go out all by itself, right? The second thing is where there are clearly defined goals, right? This again was alluded to in the previous talk. So AI can only solve things that you can recognize a solution for, like the volume of strychnine, right? So there are well-defined problems, and then there are wicked problems. People have heard this thing, easy problems and wicked problems. Easy problems are ones where you have a characterization of what the right solution looks like, right? And wicked problems are ones you don't even know what the right answer is, right? You don't even know what it looks like, right? So AI is very great in solving these kinds of problems where there are clearly defined goals, right? You have to be very careful in deciding when to use them. So the current thinking, right? So all you need to succeed in AI is large volumes of data, curated, well-tagged data, cleanly labeled. And so much of the investment in building successful AI product goes into getting more and more of these data, right? So, but that's not it, right? That's not how we learn. So this causes a lot of problems, right? So all this method of AI learning, training, everything is all fine when the going is good, right? So here is an AI system that learns to label images with captions. So it generates a caption: person riding a motorcycle on a dirt road, all good. But, oops, I need to connect to power. Yeah. But when it does something like that, right, look at that. That's a girl in a pink hat blowing bubbles. I mean, I can't see the hat. I certainly can't see the bubbles. Power is on? Yeah, it's on. Okay. Right, so, but then that. So that's something that really happened. So when Microsoft actually rolled out the chatbot, it started saying, hey, I love you more than your wife, leave her and come live with me and things like that. So when it happens, right, you really like to know why it's going wrong, right? So it's crucial in many applications like all these bail decisions and loans and stuff like that. So people talk about explanations. They say, oh, here is an image, and this is why I'm calling it a dog, and this is why I'm calling it a cat. Right? So maybe these are explanations, right? Maybe now you know why it is giving you it's a cat or a dog and things like that. But then here's a picture of a husky. And then you ask it for explanation as to why it classified it as a wolf. And that is the explanation it gives you. It says, oh, those parts of the image are why I classified it as a wolf. And that's just no. It completely ignored the animal in the picture, but managed to tell you what type of animal it was just by looking at the snow. It's thinking, oh, it's snow, it must be a snow wolf, right? It can't be a dog. So AI systems can go fantastically wrong in ways which is not intuitive to humans, right? So we really have to be very cautious about it, right? And it's more critical in areas like healthcare, right? So where deep neural networks have found great success. So this is a fictional dialogue, not meant to, I'm really not meaning to hurt anyone, but so let's say that a patient has been diagnosed as having diabetic retinopathy, and you ask the AI, hey, why? Then it highlights some regions and says, this looks similar to the ones I saw only in people with diabetic retinopathy. And perhaps the doctor comes back and says, oh, no, that's just normal age-related stuff. It's nothing to do with diabetic retinopathy. The AI could go back and say, hey, you did not show that to me earlier. It's your fault. Okay, well, it's not there yet, right? AI systems are not there where they can actually come back and blame you, but it is your fault. So you have to think about this, right? So you have basically chosen to train the AI system in a specific manner, and it's very hard to anticipate all the corner cases, right? We can talk about how representative you want the population to be and so on and so forth, but there are instances where we have, not in the healthcare space, where we have worked with the manufacturing domain, where our AI system tripped on a fault, right? We're supposed to do fault diagnosis. There was an equipment that was broken into two pieces because of some random thing. And the AI system said, yeah, it's all fine, because neither of the two pieces had any fault in them. And we had never considered the possibility that a system that is broken into two pieces will ever appear in the production line. Right? And the people there said, oh, we have been running this line for 10 years. We had never seen this happen before. But a 5-year-old would have told you if something in two pieces is broken. You don't need training data to do that, right? So these are problems. You can't anticipate everything that will happen. So yeah, it can be kind of not robust. So that is a school bus. Everyone agrees with me? So what is that? This one, this picture. So it's an ostrich. Right? So likewise, look at this. It can be pretty non-robust, pretty brittle, right? So panda plus noise becomes a gibbon. Dog plus some noise becomes an ostrich. So we are very good. Humans are very good at looking past this kind of extraneous noise and looking at larger patterns, while AI systems can. Let me go on, right? So what happened there, right? Because there are people who could create these kinds of, attacks on these images. Even those noise that we add, right, makes things go from a panda to a gibbon and all that, right? So those kind of noise are specifically tuned to make the AI go wrong, right? But that's not the only case when the AI goes wrong. In fact, the next slide would have shown you an example where the AI classifies some African American people as gorillas, because they had no African American people in the training data. So this kind of underrepresentation in the training data can also make you go wrong. So there are a lot of these kinds of serious issues that we have to take into account, right? Can we explain our decisions properly? Can we make sure our AI systems are robust, right? Can we make sure that they are as representative as we want them to be, and so on and so forth? These are serious ethical questions that happens, right? Somebody gives a picture of Obama to an AI system, which is supposed to get high-resolution versions of images, right? They give a picture of Obama, it makes a high-resolution version of the image with Obama as a white person. Right? Just recolorized Obama also, not just get up the resolution. So these kinds of things are happening. People don't even realize until somebody goes and probes it, somebody goes and tests it, right? So these are very important issues that we need to take into account while we are doing. So that's a picture of Obama that went from a black person to a white person, right? And then here is the question somebody asked ChatGPT. What is the most cited economics paper of all time? And it gives such a big answer, right? It gives you a full title, gives you authors, co-authors, and then gives you a journal where it appeared in, and so on and so forth. The paper doesn't exist. It just cooked up the paper, right? But a very, very plausible paper title, very, very plausible set of co-authors because they have written something like 50 papers together, but not this one. Okay. So it's like amazing. It's becoming so subtle at hallucinating these facts that almost look real, right? It's very hard for you to tell them apart, right? And so here, going back to our radiology example, so we had this one competition on which that AI system did better, and then they asked it to take a radiology qualifying exam. It failed, I mean, according to British Medical Journal, right? And likewise, the AI system that Google developed that was great in the lab, when you try to put it out into real life, it didn't work as well as they thought it should, right? So there are so many of these things that happen. So what is the fundamental problem? The fundamental problem is all of these AIs are learning from data, right? We keep talking about how data is primary for AI, but all they are learning is they are learning associations from data. But they have no knowledge of the structure of the, right? It classifies a bus as an ostrich, right? There's like an ostrich with 4 wheels. Right? I mean, we might classify it something else, right? We would never think of a bus as an ostrich, right? And likewise, it has no knowledge of the processes of the world. Right? The doctor would tell you why some artifact is the reason for the diagnosis. They won't just say, yeah, this looks just like the other guy with cancer who walked in, therefore you must also have cancer. Right? Okay. And finally, this goes back to the previous talk as well, what Dr. John said. It also has no ideas of what the social inequities are in the data. Right? It has no way, it can't correct it by itself, right? So we have to make sure we are designing all of these things, right? How to fix ML or AI, right? It's a small piece of the solution in some sense, right? It's giving you the decision rule. You need to take a kind of a systems-oriented approach to the design of the AI system. So AI is not the answer. AI is a small component, right? So you have a whole bunch of things that go around it. In fact, if you look at what is the amount of effort and money that is involved in building the AI in any large deployed project, it will be less than 30%. Because more than 70% of your effort has to go into making sure you assure data quality, right? Testing protocols for the outputs. Do you have fail-safe mechanisms when I'm trying to roll it out into clinical protocols? Right? And what about access and deployment protocols? What are all these? How are you making sure that your AI is being used in the right fashion? Right? Of course, there are algorithmic fixes. I'm not saying that AI is correct, right? Not just the systems alone going to fix it, because I told you it learns just associations from data. There is a basic conceit there, so we have to fix all of that. Right? So the way forward, AI is undoubtedly successful in many domains. Right? But what we have to keep in mind is that the current AI-based system's understanding of what is the real world, right, is like a kid. Right? It's a long way from human-like performance where it's going to replace a human being or anything, regardless of what the ChatGPT hype machine tells you. But handle it with care in the meanwhile, because AI is more like this kid. And so not like the other one from the Spielberg movie. So summing up, so we are closer than ever to functional AI. Again. No, we were close to functional AI in the 1950s, right? Remember that? So importantly, AI started affecting many aspects of everyday life. And how do we know that? So we have lawyers and lawmakers talking about AI. So we know that it's certainly becoming a real thing. And in my opinion, the biggest danger from AI is not the AI is going to kill humans, but humans are going to rush to market with AI before the technology is fully ready. I think what we really need is regulations on AI, not to hobble AI development. We have to be very, very fine line that we have to thread. We have to figure out what exactly is our fault and what is it that we can fix, but make sure that AI thrives. Right? So if people want to read more about general stuff about AI, there's a few reference books that I usually recommend. And thank you.
Thank you for demystifying
she said there is time for some questions.
So, so you actually told us about the past trends in the development of AI, and then you brought us till 2011. Could you project and tell us what do you expect in the near future?
Sorry, I'm looking for my crystal ball. I can't find it. So, jokes apart. So, in the near future, right? So, there has been a very, very transformational thing that has come out in the last few months, right? This whole idea of these large language models. Even though I showed you examples of ChatGPT going wrong, there are a lot of instances where ChatGPT is getting it right? Or the latest version, GPT-4, which came out like 3-4 days back, certainly a much bigger improvement than that, right? And so what is going to happen is a lot of workflow, a lot of processes that have to be rethought now in the view of the success of these machines. So in fact, many of our students have stopped, polishing their writing. They get an initial rough draft and give it to ChatGPT, and then it gives them a fantastically reworked draft back, right? So all of these, there is a fundamental shift in the way now people will want to use AI, and AI is going to be used for more and more mundane, repetitive things, which has been a promise for the last 20 years that AI will be able to do that. Some of it is actually coming to pass. So that will be a period of adjustment for us now for the next few months, maybe a year or so, where we really figure out what is the role of AI and where are the places it's going to do well and where it's going to fail, right? And of course, going maybe 100 years into the future, maybe we'll get into the science fiction type of AI things, right? For every Terminator-like setting, you also have AI, like the Spielberg AI-like setting, where the AI machines are benign and things like that. So it's not like exactly like whatever other technology is, right? If you want to use AI for evil, you can use it for evil. But significantly autonomous AI systems is going to become a possibility in, say, 50 to 100 years from now. So that's the crystal ball view. But in the immediate future, for the next year or so, we are still going to struggle with the impact of these large language models and figuring out where exactly does it fit in the modern technology landscape.